the reason why I split chapter 5 into two larger assessments is there's so much in chapter 5. There really is. And one of the next things that I'll teach you guys is called the fundamental theorem of calculus, which is like one of the like building blocks of what we do. What I want to do, like my intention is to like clean up all the stuff in chapter 5 beforehand. Then I'll teach you guys fundamental theorem of calculus and how we can actually use it in practical application afterwards. So that's why I split it into two. But the last section that we're going to do today, definite integral, is, like I said, I think it's of the ones that we did in chapter 5, this is probably the most simple. But I guess let's not get ahead of ourselves. We'll see what you guys think. So we very briefly looked at number 33, and that was one of our area problems. And when we did 5.4, I mean, we had like a massive area problem at the end, like Tarun was talking about. And we did this one example that took us a long time because there was a lot in there, okay? And basically what we were doing is we were chasing around the definition of area, of net signed area. So, we talked about like starting the process with finding x sub k star, and then we plugged it into our function, and then found our delta x and multiplied it by that as well too. And then ended up with this. And then we did, like Tarun would call it, kind of like a proof kind of thing, where we like multiplied everything out and then actually took the limit of it. The only ones that we can take the limit of are ones that we have a rule for, like Ashley asked about earlier. I never gave you guys anything for cosine. It's just things that, just polynomials. And you see how much work it takes to actually simplify one that is a polynomial, okay? I wouldn't say this is out of reach for what I could ask you guys to do, but remember, none of these steps were difficult. It was all just like simplifying and then taking all the terms that don't involve your iteration, moving it outside of each one of your individual sums. And then, we had to use some formulas here in order for us to actually find what that limit was, okay? All right, so I do have one more of those. I would like to do that if we get time to it, but let's go ahead and look at what we're doing in 5.5, okay? So in 5.5, we're going to come up with an easier notion of how to find area under the curve, and that's what we'll get at when we talk about fundamental theorem of calculus next, okay? But we can update our definition and notation for net signed areas. You guys have used it a little bit already. But again, if we have a function that's continuous on a closed interval, then it's got to be integrable on that closed interval, and the net signed area is defined as follows. So this part of the definition I just brought up again from our definition on Friday. Nothing has changed there. The part that we're focusing on this time around is the part that's all the way to the right. So this part right here, okay? You've seen that symbol a couple of times before, whether it was in like AP practice that we did or just, different places in the past. I'm sure you guys have seen this. This long, skinny S that's right here is our integral symbol. And what it represents is us taking our antiderivative. And we've seen that before, okay? What's different now is that I tag some numbers along that integral symbol. So we've got an A and we've got a B. And what this indicates is us finding the area under the curve on that interval, okay? All right, so the right side, the part that I have boxed in red, is what we call our definite integral of f from A to B, okay? So the numbers A and B are called the lower limits of integration and our upper limit of integration, okay? And let me take attendance, okay? All right, so what we can do then instead is we can, instead of writing this as the limit of a sum, we can then instead write it as using our integral symbols, and it's much easier to write and work with in that case. I knew it was coming. I tried to get it by then, but...
Will you please take it? Thank you.
Okay. Your rule is just going to represent your function, and then your limits are going to be represented by the interval that they give you as well too. Okay, so instead of going through that process, similar to those last examples in last section, we can just write this instead as the integral from, so our limits are just going to be taken from our interval, so we would say from 0 to 4. And then inside of here goes what our function is going to be. Okay, so instead of x sub k star, we would just replace it with an x. So this looks like 6x times quantity, 4 minus x to the second power. And then instead of delta x k sub star, we would just write dx. So that is what our notation is going to look like going forward. Okay. Now again, what that represents is that still represents the area under the curve between the function that's given and the interval itself. So between that function and the x-axis. Okay. Previously, we referred to this as net signed area. We're still going to call it that way for now. Okay. And in the past, like in other math classes, you guys have always thought about area as being non-negative. But we talked about how to find area using rectangles. And since the heights of our rectangles are going to be negative, we have no choice but to view this area as negative values in some of our instances. Okay, so any area that's above my x-axis is going to be positive area, and then area that's below my x-axis is just going to be negative area. And how we can think about this in application is like when we talked about position, velocity, acceleration. Anytime that we had that we went from position to acceleration, take the derivative of position to get velocity, take derivative of velocity to get to acceleration. So then if I want to work back up the ladder, I would have to integrate in order to get from acceleration to velocity and then from velocity to position. And that's coming in the second part of chapter 5. However, we viewed negative velocity as, negative movement. So movement in a negative direction. So then if we want to go from velocity to position, I would take the antiderivative of that. And if it's negative, then that shows me how much movement I've moved in a negative direction. Okay? And then, we also can have a case where if we're talking about like displacement of fluid in a tank or something like that, like our final value can be less than an initial value. So that would give me a negative area or a negative net change. Okay. All right. So like here's a function such that, if I take my area from A to B and I broke it up into a bunch of different intervals, depending on how I assign those rectangles, if I did it like in a very rudimentary way, let's say I did it using like left endpoint. And I've got some area here, and then here to here. Okay, so I would have, if I use my highlighter tool and I think about this as positive area there, and then I have a little bit more positive area there, but I've got negative area there. Okay, so our net area under the curve would be our area above the x-axis, if I think about it truly in a positive fashion, and then minus my area below the x-axis. That would give us our net signed area. Okay, so basically what I'm telling you is it is possible for you to have negative area values. Okay, typically this is not something that we have to pay too close attention to once we get to the second part of chapter 5. But in this section, we've got to particularly think about it in terms of a graph, okay? And again, that's just represented by the area or the integral from a to b of f of x dx, okay? All right, so let's actually do some examples where we work with area, okay? All right, we're going to start by using geometric formulas. So we'll do a bunch of examples where we look at this geometrically when we want to find the area that way, okay? All right, so what this is telling me, this first one, is I want the area under the curve between the x values of 1 and 6 of 2, okay? So if I look at where 1's going to be, looks like I'm starting here. My other bound is right there. So I want to find this area under the curve. Why did that happen? So I want to use this area under the curve. All right, now, what shape is that? So I just want to do base times height. So the integral from 1 to 6 of 2 dx is just going to equal, what's my base? Good. And my height? Cool. So then 5 times 2 gives me 10 units squared. All right, another one. I want to find the area under the curve between the x values of -1 and 2 of our function x plus 2. Okay, so -1, let's say, is here, and then 2 means we are finding this area. What shape is that? Yeah. Anybody remember our formula for a trapezoid? Yep. Sum of the bases times height divided by 2. I always write it as 1/2 base 1 plus base 2 times my height. Okay? Believe it or not, trapezoids are going to become very important in this course. Yeah. So get excited for that. All right? Now, how we view this is we're actually going to take this trapezoid and we're going to rotate it 90 degrees and think about it like this instead. All right, so integral from -1 to 2 of x plus 2 quantity dx is going to equal 1/2. All right, I need to find my height at this value and then my height at that value. So this just represents the coordinate point -1, 1. And then this represents the coordinate point 2, 4. All right, so base 1 plus base 2. Base 1 is going to be a height of 1, and then base 2 is going to be a height of 4. So I'm going to have 1 plus 4, and then times my overall height, which is the difference from 2 and -1. So 1/2 times 5 times 3. So 15 halves units squared. Okay. All right. Let's do the last one here. Okay, so from 1 to 3, so let's say 1 is like here, and then it's probably not super accurate, but let's see. If I plug in 1, I get an output of -1. So let's say that's -1, 1. And then if I plug in 3, I get an output of -7. So let's say like right here. All right. So I want to find the area that is bounded between my function and then the x-axis at those values. Okay. So what that looks like is this. Okay. What can you tell me about that area? Definite trapezoid. What else can you tell me about it? Let's find out. What's the length of my base 1? So if I take this and I rotate it, we can think about it like this. No, it's fine. Do that. That's cool. All right. Now, my bases are still going to be positive. So base 1 and base 2 is still going to be positive. My dimension that's going to be negative is going to be my height. Okay? All All right. So my change in my x is going to be 2. So we're going to say my height is negative 2. And then my outputs, oh, I wrote this first coordinate wrong. Very wrong. 1, negative 1. All right, we're going to consider our outputs to be positive. So we're going to say 1 and 7. The other way we could think about it is we could make each one of those base 1s and base 2s, since we're rotating it. We could keep those values negative, and you could keep your height positive. All that matters is that one of your values is positive and one of your values is negative, okay? One of your dimensions, rather. But our area, since it is underneath the x-axis, is going to give us a negative value, okay? All right, so 1/2. All right, our base 1 and base 2, we're going to say 1 plus 7, and then we're going to give it a height of negative 2, okay? I actually think it probably makes more sense to think about your base 1 and base 2 being negative, since that's what's going down in a negative direction. But one of them being negative and one of them being positive is going to give you the same answer, okay? All right, so when you multiply those, what do we get? Negative 8 units squared. Yeah, I actually think keeping our base 1 and base 2 negative would be better, okay? But it all washes out to be the same, okay? All right, let's look at some more areas. Okay, now let's do, our function is x minus 1, and we are bounded by the x values from 0 to 2. So we've got 0 and then 2. So you'll see that we have some positive area and we have some negative area as well too. Both triangles. So we're going to have 1/2 base times height plus 1/2 base times height. So the area of my two triangles added together. Since we have two distinct triangles, I think it's worth us, of course, splitting it up into two different ones. All right. I don't necessarily have to rewrite it, but I will. X minus 1 dx equals, okay. So let's do the area of our first triangle, okay? So 1/2, its base is again going to be 1 minus 0. My height, we're going to say, is -1. So height of -1, base of 1, plus 1/2, and then the base of my second triangle would be 2 minus 1, and then its height would be +1. All right, so we get -1/2 plus +1/2, giving us a total net area of 0. Some of it's positive, some of it's negative, so they will cancel out, and it will indeed be 0. Okay. All right. What's our last shape here? Semicircle. All right, so again, that's indicated by square root of 16 minus x squared. If we set that equal to y and solve for 16, essentially, you would get the area or the equation of a circle pretty easily, okay? But we are bounded from -4 to 4. It's going to look something like that. All right. So what's our area equation that we're going to use? Good. Times 1/2. All right. So easy enough. 1/2 pi, what's my radius? 4 squared. So 8 pi units squared. All right. It is a decent amount of this in this section. Let's do one more area problem like this. I lied. We're going to do two more. Oh, this first one, I don't even know. I don't feel as if that's necessary. So integral from -4 to -1. So that would just be here to -1 would be there. We just end up with a rectangle. So we can have a total net area that's going to end up being negative. So we're just going to do base times height. So our base would be -1 minus -4, and then our height is going to be -5. So -1 minus -4 is going to give me 3 times 5 times -5, rather. Gives me an area of -15 units squared. So maybe we didn't see a totally negative area, but there it is. All right, last one. So we've got this piecewise function here, and we want to find the area between the curve and the interval from -2 to 2. So I've got that triangle there, and then this other triangle here. So let's say some of it's going to be positive, some of it's going to be negative. So we've got this area that's going to be negative, and then we have this area, which is going to be positive. So if I want to find my total area, I'm just going to add together 2 triangles. All right, so if I find my coordinates of each one, if I plug in -2, that goes in my bottom function. So this is going to be -2, -1. This is going to be, so where is that actually going to be equal to 0? That's going to happen at -1, 0. And then this height looks like that's going to happen at 1, 2. So if I plug in 1 into my top function, I get that that's going to be 2. Okay. All right. So area of my red part, my base is going to be -1 minus -2. And then my height is going to be -1 plus area of my positive rectangle, 1/2. That base is going to be 2 minus -1 and a height of 2. So then I would have -1/2 plus 3. So then 2.5. 5/2 units squared. Okay. All right, questions there? We did a lot of area. All right, here's a bunch of properties of definite integrals, and most of them I do not believe will be surprising to you, okay? Some of them are defined in your book as definitions, so definition 5.5.3, which I believe is these two right here. So I think that's 5.5.3. I call them out because I think in your homework it says, hey, use the definition of definition 5.5.3 in order to evaluate these integral using these properties. It's just these properties here, okay? And then the rest of them are broken up as different theorems, okay? We actually had this first one already. The integral from a to a of f of x dx. There's no base to that, so that's just going to be 0, okay? All right. If I take the integral from b to a of f of x dx, notice what's changing to the right side of my equation. My limits change. So instead of going from the integral from b to a, that would be the integral from a to b, okay? What that effectively does is it changes the sign of your base for the area that you are finding. So to compensate for that, we toss an extra negative in front of our integral there, okay? That'll come up pretty frequently, all right? We have a theorem for the third one. Initially, the theorem says if c is some number between a and b, then the integral from a to b of f of x dx can be broken up as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And essentially, that's what we are doing right here. We're taking the integral from -2 to -1 of f of x dx, and then we're adding to it the integral from -1 to 2 of f of x dx, okay? So that's using that third property right on that previous example that we just did. We just broke it up into two areas and added them together, okay? Now, this also holds true for any C value. So C doesn't even need to be between those two values. C could be beyond the values of A and B in the interval, okay? But that area still works out to be the same, okay? Because what you'll find is some of it is negative area and it just negates the difference between the two, okay? All right, the fourth property should not be surprising, bless you. I mean, we've seen this with limits of sums. So we saw that if we had the sum from k equals 1 to n, whatever, of some value times a function, you can just pull that value outside of your integral. We can do that with derivatives. We can do that with integrals as well too, okay? And then the integral of multiple terms added, multiple functions added or subtracted from each other is just equal to those integrals separately added together as well too, or subtracted from each other, okay? So you can split apart functions, expressions, using multiple integrals is what property 5 is telling you, okay? And then 6 says if your function's integrable and non-negative, so if it's always above the x-axis, then the area under the curve will be positive, okay? And then if f and g, two functions, are both integrable on the interval, and f is less than g, then that means the area under the curve from a to b of f is going to be less than the area under the curve from a to b of g. So that's what that last property is saying, okay? These problems tend to be nice because working with these properties is pretty simple. All right, so let's do some of that. I put one example in here. Probably could have put another one, but you guys will get some chance to practice with this tonight. All right, so given the integral from 0 to 3 of f of x dx equals 4, and the integral from 3 to 6 of f of x dx equals -1, let's evaluate our following integrals. So essentially we use both of these as reference in order to find what we want, because we don't know what f of x is. So the best we can do is just use them as reference, okay? All right, I don't know what 0 to 6 is, but I know from I know what 0 to 3 and then 3 to 6 is. So I can say this is the integral from 0 to 3 of f of x dx plus our integral from 3 to 6 of f of x dx. We kind of saw how this was similar to sums, and we talked about like breaking, like remember when we had a sum that started at 3 instead of 1, and we wanted to use our formula with it. So we did the sum from, 1 to n, and then the sum from 1 to 2. So we like stopped before that value, but we want every morsel of area instead of working with integers. So that's why we do it at that same value that it starts or stops at is when our next one is going to begin at, okay? All right, so when I add these together, I would just get 4 plus -1, giving me a total net area of 3. I do want that, yeah. You're gonna run into your class period.
I'll be like super fast because I know it so well.
Okay, what property should I use for the second one? Yeah, let's flip it, right? So toss a negative in front, and then it's going to be the integral from 3 to 6 instead of f of x dx. So that is negative times -1, which gives us +1. All right, what about C? 0. All right, last but not least, D. Good. So -5 integral 3 to 6 f of x dx is equal to -5 times -1. Man, I thought I put another one in here. I don't think I did. Shoot. That's okay. I had one where we had like some sort of function, and it looked like this. I really thought I put it in there, but I guess I did not. And we're going to say that this is our function f of x. Whatever, 1, 2, 3, 4, 5, 6. Okay. And then I'm just going to say this goes down to -3, I guess. So let's draw a quick little piecewise function here. And then if I give you something like this, I could say, hey, find any one of these values of these integrals. So we could say like integral from 0 to 1 of f of x dx. Or integral from 1 to 3 f of x dx. Let's say integral from 3 to 5 of f of x dx. And then we could say, I don't know, integral from 5 to 6 f of x dx. And then integral from 0 to 6 f of x dx. So I went a little crazy with this one, sorry. I thought I put one in there, but I must have forgotten to paste it. So given this function, we can find the area between the curve and the interval itself using these values. So what's my first value going to be? So integral from 0 to 1 of f of x dx, we're talking about this area right there. So it's going to be a triangle. All right. So then 1/2, our base is 1, our height is 2. So we get 1. Super. All right. Let's do our next one. So that's from 1 to 3. What shape is that? Okay. So my base is going to be 2, and then my height is going to be 2. That gives me an area of 4. All right, and then we're going to do the integral from 3 to 5. So that's this area as well as this area. Oops. So I'm going to have two triangles there, right? Some positive and some negative. Okay. All right, so my first area is going to be 1/2 a base of 1 times a height of 2. Plus my second area is going to be 1/2 a base of 1 again times a height of -3. So it gives me 1 minus 3 over 2. So -3 over 2. Or no, -1/2, my bad. Okay. And then let's do 5 to 6. So then 5 to 6 is going to be from here to here. Okay, so then that's triangle. 1/2, my base is going to be 1, my height is going to be -3. So then that's another one that gives me -3/2. So then what would I do for my area from 0 to 6? Yep, and I conveniently did it in such a way that it's completely partitioned. There's no overlap between any of those. So I would just need to add all of them together. So 5 minus 2 gives me an area under the curve of 3. All right, questions there? Was this the easiest one we did in 5? I feel like it was. We'll see when we get to the homework, right? But for the most part, it's just, geometric area and then some properties as well too, okay? All right, so homework is on the last slide, but I want to go back and do that other example that you guys saw at the end of 5.4 that we never fully did. All right, so let's go back and do that. Okay, so getting back into what we were doing in this section. We're doing net signed area, so we're using this formula, as we saw before, in order to find our area under our curve, okay? Now, with this one, so there's our function, cool. We can find our change of x from that pretty easily. We need to use left endpoints. So from the previous slide, our left endpoint formula is there. X sub k star equals a plus k minus 1 times delta x. Also on the board as well, too. Okay? All right, so x sub k star equals, okay, so our a value, which is conveniently just 0, plus k minus 1 times our change of x, okay? Change of x, so we're working over the interval from 0 to 2, so it's just going to be 2 minus 0 over n. So we just get that that's equal to k minus 1 times 2 over n, okay? So then, of course, change of x, we just computed to be 2 over n. So then now what we want to do is we want to plug that stuff into our function and then take our limit of our sum. So limit as n goes to infinity, sum of k equals 1 to n of, all right, so then we need to throw that into our function. So 2 times quantity, k minus 1 times 2 over n quantity squared plus 10, and then multiplied by our change in x, which is going to be 2 over n. All right. Okay, so we start expanding this out. So limit as n goes to infinity, sum of k equals 1 to n of, okay, so I'm going to start by squaring. So 2 times k minus 1 quantity squared times 2 over n squared, and then plus 10 times 2 over n. Okay, so then in that case, let's square out k minus 1. Okay, so we get 2 times k squared minus 2k plus 1, still times 2 over n quantity squared plus 10 times 2 over n. All right, so each one of those terms is going to get a 2 over n squared on it. But thinking about what we did in the last example, everything involving n we just tossed in front of our sum. So I know this is going to get multiple sums at some point. So I'm just going to break it up by pulling these pieces out, okay? All right, well, let's see. Two is multiplied by all of this. There we go. I have to put a set of parentheses right there. So a set of parentheses that I just put in, that still needs to be there. Okay. Well, those things are multiplied by each other, so, but that's okay. It keeps our thoughts organized. All right, so let's see. Limit n goes to infinity. Most efficient way to do this, let's just distribute 2 over n squared to each piece and then a 2. And then we'll just take the sum of each piece. So then k equals 1 to n. Okay, so for our first term, we have k squared times 2 over n squared. All right, so then let's just say that, and then all that 2 over n is going to be in front as well too. Okay, so then all that is going to be 8 over n squared times k squared plus, okay, and then so each one of these is going to get an 8 over n squared on all of them. So I really just put that. And then there's another 2, but I'm going to put a subtraction sign there. That's minus, sorry, not plus, that's minus. Okay. All right, so then, and then there's also a 2 times k there. So let me actually change that 8, instead of an 8, because I forgot about this 2 right there. Let's make it a 16, right, instead of an 8. So that's 16. And then times k. And then I have 2 times 1, and then 2 over n squared times 1 as well, too. So then we would have just 8 over n squared. And then I still have plus 10 times 2 over n. Don't need that parenthesis there. Okay, we're fighting through it. But we're almost there. Okay. None of these terms are alike, so we're going to get a sum for each one of them. So then sum k equals 1 to n. Okay, so let's do a sum for our first term here, not forgetting that it's still multiplied by 2 over n. So this 8 over n squared is going to go in front, but I'm going to hit it with this 2 over n that's there as well too. So we're going to put 16 over n cubed in front. Minus, all right, so let's do our next one. So then 16 over n squared is there, multiplied by 2 over n. All right, so then 32 over, oh yeah, I forgot the k squared, got it. Thank you. Okay, so then minus 32 over n cubed. Sum from k equals 1 to n. All right, and then of k plus, all right, so 8 over n squared hit with 2 over n, 16 over n cubed again. And then sum of k equals 1 to n. I pulled everything out, so I'm just going to put a 1 there. And then last but not least, 2 over n times the sum k equals 1 to n of 10. Something doesn't feel right with this one. I feel like I may have made a mistake somewhere. I don't think so, though. I don't know. Let's find out. Now we plug in our formulas for each one. So limit as n goes to infinity, 16 over n cubed. And then we have our formula for k squared, which is n times 2n plus 1. No, n times n plus 1 times 2n plus 1. N plus 1 times 2n plus 1 over 6. All right, minus 32 over n cubed. I feel like that's a mistake. And then times our value for k, which would be n times n plus 1 over 2. And then plus 16 over n cubed times our formula for 1, which would just be 1 times n, so times n. And then plus 2 over n times 10, which would be 10n. All right. And then one thing I suggest to you guys, the rest of this can go fast, is take your denominators and swap them for each one of your terms. So 16 over 6. And then on the inside, I showed you guys how to expand that out previously, but I think you get 2n cubed plus 3n squared plus n. I think that's what that ends up being. And if you don't feel like expanding that out, that's okay, because you know that when you do expand it out, your numerator is going to have a degree of 3, and your denominator also has a degree of 3, so we're actually going to get a limit out of that. Here we get 32 over 2 times n plus 1 over n cubed. However, what's going to happen to that piece when I take the limit? This should be 0, right? Because up top you get n squared, and in the denominator you get n cubed, so it's going to be 0. Plus 16n over n cubed, that's going to give me 0 as well too. And then this final one is going to be 20. So then when I take my limit, I get 16 thirds out of my first piece. So this goes to 0. This goes to 0. And then plus 20. So then 76 thirds would be our area. If you see a problem like this on your quiz, I would make it easier to deal with. I think it's, I don't know. It's always going to have a fraction. Yeah. One thing that makes it easier is when your first value is 0, which this was here. So that's one thing that could make it a little easier. But aside from that, like, I also feel like I didn't go about that the most efficient way. I don't know why I didn't, but it takes a minute. What's wrong, Rhea? Okay. Are you feeling uneasy about this?
I just need to look at it slower, and then I should be fine.
Sure. Well, as a recap, and not just for Rhea, but for everyone, as a recap, start by, we've got our function, and then we've got our interval. And then from there, it was based on, left endpoints, right endpoints, or midpoint as well, too. I'm not going to give you one that would require you to do midpoints. I would instead be much more apt to give you like a left or a right, and a right's the easiest. Because then that formula, there's no k minus 1, it's just k, which makes everything much easier. All right? Okay, so be prepared for doing some sigma notation sums. Know your formulas for, a constant, I squared, I cubed. And then from there, it was just kind of finding some sums. Okay. I don't know. That's just like a concept to know. You got to spot them, right? Yeah, we're going to do tomorrow. We're going to do tomorrow. Test still Friday. The hardest test in the school is what Mr. Shane said? What's it over?
Like, charges, potential difference. It's like.
Do you guys deal with any imaginary values when you're dealing with charge? And have you talked about electrical fields yet? You said what?
Yeah, everything's theoretical. None of it's real.
Yeah.
Like the scenarios are so fit.
What period is this?
6.
Yeah, I wanted to come observe that class.